There we go. So good morning. It is, what is it? March 18th, 2023. My name is Whitney Garner. I am a GRE GMAT executive assessment instructor at Manhattan Prep. And this morning, so here on the East Coast, I'm in North Carolina. This morning, our free prep hour, let me get my screen shared. Our free prep hour is going to be all about work problems. So we often lump these together into rate problems and work problems. I generally think of them as two very, and in fact, actually three very different types of questions. I think of there are some rate problems that are like distance rate time. I handle those almost exclusively by drawing pictures. We've also got kind of rate problems that more often I might call conversion problems, where you're converting things like miles to hours to centimeters per second, right? Like that, those I would just call more conversions. But then there's this third type that I think give people a lot of trouble that are work problems. And they really come in one of three flavors. We're only going to play with the two hard flavors. We're not going to deal with the sort of more straightforward one. But generally speaking, when we start to look at work problems, I want to sort of list them out for you, the three types of work problems that you might see. So the first type would be a single person or machine or what have you doing a single job, right? So a single person doing a single job, right? Like one person building a birdhouse. It seems like it's always birdhouses. I don't know why. We're going to have several birdhouses in today's lesson. But it'll be just like one thing doing one job. A person performs at a certain rate. So for example, let me give you kind of a little simple version of this, right? And we'll try it, but then the rest of the time we'll look at a more complicated version. So a single person doing a single rate would look like the following. Okay. So our fundamental formula, generally speaking, for, Malik is painting this much of a room. He's able to do it in this much time. Working at that speed, how long is it going to take Malik to paint one whole room? We're going to use the basic formula: work is equal to a rate times a time. So work problems, I either use a formula or a ratio. And we're going to have two formulas and one ratio that we're going to utilize today. And so this is the most basic formula. We use this when we have a single person or a single machine doing a single job. Or we put the amount of work, we put what their rate is, where a rate is an amount of work over time, and an amount of time. Yeah. And so I want you, and you might have to use this equation more than once in the same problem, but all we'll ever do is use this basic formula. So I'm going to give you about a minute and a half and pull in with an answer. If you're here in the room live with me, pull in, get you a little stopwatch, what you think the correct answer to this problem is. Okay. All right. So send me an answer privately if you haven't already. Yep. Great. So, and then note, yeah, beautiful. So when we've got our work equals rate times time, we're really only going to use this for a single machine or a single person. So our first expression tells us that Malik can paint 2/9 of a room. So that's an amount of work, 2/9 of a room in 40 minutes, right? And so the answer choices are given in hours. So we might want to consider, what is 40 minutes in hours? It's 40 minutes over 60 total minutes, or it is 2/3 of an hour. So Malik can paint 2/9 of a room in 2/3 of an hour. It means that we're missing rate. To find the rate, we're going to multiply both sides by the reciprocal. That's how we get rid of fractions on one side, multiplied fractions. So we're going to multiply both sides by this reciprocal. And so this 2 and this 2 and this 3 and this 3 cancel. We get a little canceling over here. This is 1 and 1. This 3 cancels this 9 with 3. So Malik's rate is 1 room every 3 hours, right? We can then plug this back into another formula if we wanted to solve for how long it's going to take Malik to paint 1 room. But if we remember that a rate is a work over a time, then what we've got here is 1 room every 3 hours. So anytime you have a rate and a fraction, you're actually already in a work over time. And so how long does it take to do 1 room? It's going to take 3 hours. Generally speaking, you're not going to frequently see the one character working. Maybe in like a QC where you have to solve for 2 different, like how long is it going to take this person to do this much work? How long is it going to take the person to do this much work? At twice their rate or half their rate or what have you. But this is going to be the least common, I'll argue, and often the most straightforward of the work problems. So this is the only one of this type we're going to do today, right? Single person, single machine doing a single job. Generally speaking, the work problems that give folks trouble are one of the following 2. So before you start solving these, we're going to solve them separately down the road, right? But what I want you to take a moment and look at is what's different about these 2 from our friend Malik painting a room. Yeah, so take a moment. What do you notice is different in these 2 problems relative to our Malik problem? And I'll put them all on one page so we can kind of see them all together. But what do you notice? And type it in the chat window if you got an idea about what feels a little different. Yeah, there's more than one person. Absolutely. So in our Malik problem, we're dealing with a single person or a machine. And then we find out their rate might change, that one person or that one machine. It might say, here's how long it takes them to do it in this form, right? And so on, right? However, and so before you get solving, right, we've got 2 different variations on the theme. So if the bottom 2 have more than one person, what's different about from the bottom 2 from one another, right? So what makes the second one different than the third one, for example? What do you notice? What's different about the second one relative to the third one? Yeah. Okay. So when we have a single person and a single person or machine, we are going to use the form work equals rate times time. Or we'll recognize that by rearranging this, a rate is equal to, divide both sides by time, an amount of work over an amount of time. So traditionally, a rate is going to be effort over time, in the same way that a speed is distance over time, right? Miles per hour. We don't usually say hours per mile. We go miles per hour, right? Same thing here. We go birdhouses per hour, dog houses per hour, boxes per minute, rooms per minute, rooms per hour, right? So these are going to be our primary formulas. This is going to be our primary formula, but you could use either variation that you want for the single person, single machine. The second one, a couple of you noticed, is about 2, sometimes 3, right? But 2 people or machines. And the key here is working together. Now this might be 3, might be 3. Okay. So there's one other key here. The key here is that they have different rates. Okay, so rarely it is 3 that you'll have like a third person or a third machine involved. But the key here is that we have 2 people, maybe 3, and their rates are different. Okay, so we have one person, their own rate. Now we have 2 people, maybe 3, that have different rates. What we need to know in this case is that when people work together, well, what do y'all think? What do I do with rates when people work together? So if I can build 3 birdhouses per hour and, Malik can build 4 birdhouses per hour, so my rate 3 per hour, Malik's rate 4 per hour. If we're working together, how many birdhouses do we make per hour? And type it to me. Yes, exactly. So if I give you my rate, 3 birdhouses per hour, and I give you Malik's rate, 4 birdhouses per hour, and we're working together, 7 birdhouses per hour. When we work together, we add rates. The opposite is going to be true if we're working against each other. Working against each other is usually the job of hoses, right? Like one hose is filling a tub and another hose is emptying it. Let's think about it from the perspective of a work. So let's say it's Malik and me again. Malik is building 5 sandcastles every hour, and I'm coming along behind them and kicking down 2 sandboxes every hour, right? So Malik is making 5, I'm breaking 2. Every hour, how many sandcastles are completed? 5 minus 2. We subtract our rates. So when we are working against each other, you subtract rates. That's pretty rare, doesn't happen a lot. This is generally in the world of hoses, where one is filling and one is, and I'll actually kind of put this under here. This is where one hose fills and one hose empties. One fills and one empties, right? So if I'm trying to fill the tub, then the hose that's filling is working for me. The hose that's emptying is what I subtract off. If I'm actually trying to empty the tub, then the one that matters is the emptying one. The emptying one's doing the work, and the one that won't stop filling is what gets subtracted off. It's what's hurting us. So working against each other, it is almost always like this world of hoses. So I'm going to suggest, and I'm maybe a little different than a lot of people, but I'm going to suggest a method that we're going to practice that involves kind of this formula. But here's what I always know. I'm going to take the rate of the first person or machine or whatever that case may be, right? So I'm going to take the rate of that person. I'm going to add to it the rate of the second person. And if there's a third one, I'll add the third one. And that's going to get me to my rate where they work together. Now I'm going to use this and convert it if I need to. So if I'm given units of work or time, right? So if I'm not given the rate directly, if I'm given units of work or time, I'm going to actually write this as the work of the first thing over the time of the first thing, plus the work of my second person or machine over the time of my second person or machine. And I'm going to do their work together over their time together. And I want you to think of this as a formula in the same way that these are formulas. So I'm going to write this on my paper first, almost like I would an average formula or a profit formula. I'll write the whole thing down. And then I'm going to fill in blocks, right? So if they tell me how much work together, if they tell me the time for one or the other one, I'm just going to fill in what pieces I know, and I'll solve for whatever piece or pieces I don't. Okay. Our last item, and that's going to be the most complicated, I think it gives people the most trouble. And so we'll cover this in the latter half of our session. This is where we have multiple identical machines or people. Okay. So the key here is some number, doesn't matter how many, but it's multiple identical people or machines working together. Key here again, same rates. For this group, we are going to use a ratio, kind of a weird ratio of work. So we'll look at it as workers. I'll write it down, it's a little easier this way. We'll go workers to time to, or actually I'll go work in the middle, workers, amount of work to time. And so this is going to be a sort of weird ratio that we'll use where two things move in concert, meaning they move in the same direction, and then one pair of things will move in opposition. But I find it makes life way easier for most people in dealing with these problems. Yep. Okay, so we'll come back to this one. We're going to focus in, for now, on our second item here. So we'll go to this Alejandro problem, and we'll set it up. I want you to consider this as the rate of the first thing plus the rate of the second thing is equal to their rate together, which means the work of the first thing over the time the first thing takes, plus the rate of, the work of the second thing over the time of that second thing is going to be equal to their work together over their time together. So you're going to write on your paper, essentially, this line underneath this formula. You're going to take all the information from the problem and you're going to plug it in. Yeah. So let's give this one a go and let's see what answer spits out for you. And then send me your answer when you think you've got it. Mm-hmm. Nice. So notice we've got a lot of sort of complicating pieces with this one, right? If we've got two elements, it looks like we've got more than two, right? I've got Alejandro, I've got Betty, and then I've got Betty and Carrie who are working together. So there's a lot of pieces here. Okay, so let's think about how to incorporate this. The only people we have initially working together are Betty and Carrie. So I want the work of Betty over the time of Betty, basically, right? Plus the work of Carrie over the time of Carrie. And that's going to be the work of those two together. Okay, so let's take a look. I know that Betty, that's my first fraction, can build a doghouse in 3 hours. Now, often what we'll do is pick a single unit. So if it says a doghouse, a room, whatever, we'll just call that one, right? So we'll say one doghouse in 3 hours. And they can build a doghouse twice as fast as Alejandro can alone. So hold on, let's think about this. Together, they can build one doghouse twice as fast as Alejandro can, which means how long does it take them if they're able to finish it twice as quickly? So rather than think math, think logic, right? Alejandro takes 4 hours. And so they're going to take how many? Mm-hmm. Yep. Exactly. If Alejandro takes 4 hours and they can finish it twice as fast, they'll take half as much time. They'll take 2 hours. And now what we want to know is how long would Carrie take to build a doghouse? This is my missing piece of information. And you can make that whatever you want. You could just actually keep calling it the time for Carrie so you don't lose it. What I'm going to do is multiply everything through. So a fun trick for this is I'm going to actually multiply everything through by a common denominator. So the common denominator would be 6. But if I wanted to get this t out of the denominator, I actually would multiply it by 6t. So if I multiply 6t times 1/3, right, and I'll just do the extra step so you can kind of see it. This would be 6t over 3 plus 6t over t equals 6t over 2. Let's cancel stuff out. So I have 2t plus 6 equals 3t. Subtract the 2t from both sides, and t equals 6. Beautiful. Nicely done. So nicely done. So what I'd like for you to do is let's try a pair. Right? So I want you to sort of kind of like try one right after the next. And generally speaking, if these are kind of open-ended questions like this, they will have kind of a box with, how you want to answer it. Yeah. So here are 2 questions, and I want you to try them both out, and then we'll do them together. So let's take about 3 minutes for the pair. Since kind of we're just doing one right after the other, let's take 3 minutes. Send me your answer for both. All right, if you haven't yet, go ahead and give me a guess. And I want to know, how did this feel? Method feel simple enough, feel pretty complicated, hard to fill it out? Talk to me. How was that? Okay, felt okay? Okay. So we're going to set it up again. We notice that we've got machine A and machine B. We've got more than one machine working together. I look for the place where, right, like, well, my question on the first one is, are they working together? What do you think? Are they working together? There's two machines. Are they working together? No, right? Beautiful. So what I want you to start to notice is, like, hold on, these aren't working together. I've got machine A working by itself. So machine A produces 15 golf clubs per hour. That's their rate, right? So machine A has a rate of 15 clubs per 1 hour. And so they fill a production lot, whatever that means. So some number of clubs in 6 hours. So I'm going to use the work equals rate times time. So machine A can do some number of clubs. I don't know what that is, this production lot, at a rate of 15 clubs per 1 hour in 6 hours. So the work is going to be 90 clubs for machine A. Machine B fills that same amount. So now I need a new formula. This is for B. B's rate is 90 clubs every 1.5 hours. So I'm going to plug that in. How many golf clubs? That's an amount of work equals 90 over 1.5 every 1 hour. Now you've got a calculator. So for a single move like this, I might, right? Like, I might do the same math again, like just like plug it into my calculator. And so if you did, you'd get 90 divided by 1.5, which is 60, which should make sense to you because it takes machine B longer to fill a production lot. And so in 1 hour, they would produce fewer. So 60 for the first one. But the second one, notice that the question then moves to, how many bottles can both machines working together do? So I'm going to set up an expression of the work of machine A over the time that it takes machine A, plus the work machine B does over the time that machine B takes, is their work together divided by the time it takes them together. So machine A can do 60 bottles every 12 minutes. Machine B does 120 bottles every 8 minutes. How many bottles? So that's this, how much work can both fill in 25 minutes? So notice I just fill it in like it's a formula. So I'm going to clean this stuff up a little bit. I can divide both of these by 6. So that's 10 over 2, which is the same as 5. I can divide both of these by 4 to start with. And 30 divided by 2 is 15 equals W over 25. So I've got 20 equals W over 25. Multiply both sides. My amount of work is together 500 bottles. So when we're working together, we're thinking about this idea of this one, right? Like, add rate 1 plus rate 2 equals their rate together. I find that that's usually the easiest way to solve any time that they're working together. All right, so let's do one more, just like that. And I want to show you what happens when we have answer choices to use. Because technically, depending on what we're given, we also have a quick estimation way that we can, so that I usually will start with. But give this one a go, and then we'll move to the other, the final type. Here you go. All right, nice, y'all. So I wanted to show you can always set these up. Right? And you've got your calculator, so even if the math gets a little messy, it's fine. But I can do, how long will it take Wendy and Miguel working together? So I need Wendy's work, Wendy's time, or actually, right, like however I want to do it, like work of Wendy, time of Wendy plus work of Miguel over the time it takes Miguel is their work together over the time it takes them together. And so one birdhouse in 15 hours plus one birdhouse in 10 hours equals one birdhouse in an unknown amount of time. I might multiply everything by a common denominator. Here, that would be 30t. So 30t over 15 plus 30t over 10 plus 30t over t. Cancel everything out. So that gives me a 3. This leaves me a 2. So 2t plus 3t is 5t. That's an equal sign, excuse me. 5t equals 30. And so t equals 6, right? So you can get to b that way. One other thing to note, if you have answer choices, and this can sometimes be useful in QC, if I know everything on the left-hand side of this equation, so I know the two rates, that's the crucial piece. I know their two rates, then I can use an estimation when I have answer choices. And I want to think about it like this. If I had one Wendy, the job would take 15 hours. And if I had one Miguel, the job would take 10 hours. Now let's imagine I had two Wendy's. How long would the job take if I had two Wendy's? So if I could double her up, right? If I could clone her, how long would it take? Yes, exactly. It would take 7.5 hours, take exactly half the amount of time. And in the same way, if I had 2 Miguels, it would only take 5 hours. Here's the thing. I do have 2 employees, right? 2 workers, but I don't have 2 Wendy's. I don't have 2 Miguels either. I have somewhere in between those two. So I know that the number has to be less than 7.5. And so that would eliminate D and E. It has to be greater than 5. So that's going to eliminate A. And the midpoint of these two is going to be a little bit closer to 6 than 7. So I would likely choose that. I mean, 7 is much closer to 7.5 than 5. And so the midpoint is going to be, a lot closer to 6 than it is to 7. So I'd probably go with 6. The answer won't be the exact midpoint. It'll just be very close. So I don't have 2 slow workers. I don't have 2 fast workers. I have 1 of each. So the actual amount of time that my 2 workers take would be somewhere in between. But again, I love the formula. The formula always works. You can always plug things in. Okay. All right. So we're going to spend the last of our time today talking about the last scenario, right? Which is bunches of identical stuff. And you may have seen ways of solving this that involve a whole lot of formulas, and you can totally do this with a formula. The formula is a sort of extension of work equals rate times time, where we remember that a rate of a bunch of stuff is additive, right? So the rate of each one of these things added together. So what ends up happening is when you have a bunch of things, you expand this as weight or work equals number of machines times rate times time. So you could, if you really love formulas, you could use a series of formulas where you have to incorporate one more variable, because these two together, this number times rate, is essentially like adding up the identical rate for 12 machines or 5 machines or 7 machines or what have you. Now that's all well and good, but I have a method that I like quite a bit more, which is a ratio method. So the way we're going to set up this ratio method is it's workers to work to time. Okay. And one thing we want to know about these workers to work to time is that this is not a normal ratio. All 3 things do not move together, right? So for this, they only move in pairs. So I can only move 2 elements of my ratio at a time. Okay. Now, one of the things I need to know or recognize is that workers and work move together. And work in time, and maybe I'll put it this way, also move together. Think about it this way. If I have more workers, I can get more work done. If I spend more time, I can get more work done. However, workers and time are opposite. So if I have more workers, I don't need to spend as much time. If I have more time, I need fewer workers. And in fact, it is a perfect opposition relationship. So we're going to do a couple of these together, and then I'll let you try one. So the way this will work, so let me just kind of make a copy of this so we can see what it would look like on our paper. Okay, so on my paper, what I'll write, and I'll get this out of the way, what I'll write is workers, work, and time. I'll literally write this down. And then beneath it, I'll put this here in black for now. So beneath it, I'll put the actual numbers that are given, like my starting numbers. And above it, I'll put my goal numbers, my targets, if you will. Okay. So where do I start? I start with 12 identical machines, so 12 workers, running constantly at the same rate. because they always will be, take 8 days time to complete one shipment. Now the question is, how many additional machines, right? So this is, 12 plus some number. How many additional machines, each running at the same constant rate, would be needed to reduce the time required by 2 days? So same shipment, 6 days. I reduce my time by 2 days. Okay. So on the bottom, my actual numbers. I have 12 machines doing one shipment in 8 days. My goal is how many more machines. So how much more do I have to add? So I put a big box around where my like unknown is, like the thing I'm solving for. So how many additional machines can do one shipment in and reduce that by 2 days? So get me from 8 down to 6. So what we can do is move any 2 columns at the same time. I could double workers, that would double work. I could have workers, that would have work. I could double work and double time, or half work and half time. Or I can multiply and divide workers and time in opposite directions. So if I double time, I have workers. Now, this is my open end. This is the end that I don't know. And so generally speaking, that's the piece that I'm just going to let move however it wants to move. I'm going to focus on the areas that I have to have fixed. Yeah, that have to be fixed. So one of the things I can do is say, all right, my ones already are matched. They're where they need to be. So I'm going to hold that constant. I'm not going to utilize that column because it's already how I want it. I've got it there. So I need to get my 8 to be a 6. There are a lot of ways to do this, but the easiest way for me is to take it all the way back down to something basic or to something that I could then easily convert into a 6. So I need to get 8 to be smaller. So if I were to cut 8, I could divide it by 8 if I wanted to, and maybe I'll just do that. I'll go ahead and divide it by 8. So if I divide this one by 8, I need to multiply this one by 8. These 2 columns move in opposite directions. So if I divide, and then this thing stays the same, I didn't move it. If I divide this by 8, it becomes 1. If I multiply 8 times 12, that becomes 96. So here's what I know now. 96 workers can do one shipment in 1 day. I'm going to go up to 6 days. And so I'm going to multiply this by 6, which means I divide this one by 6. Right? I've held this one constant again. This is 1. This is 6. It's where I want it, right? I've got that one locked in. And now I just need to figure out what is 96 divided by 6. You won't have, so we'll do 96 divided by 6, 16. So now be careful. How many additional machines? I need to go from 12 up to 16. And so that is 4 additional machines. Yeah. So this was a wicked tricky one. Let's try one that's maybe a little nicer. Okay. So again, I want to set this up as workers. It's yours, right? So I want workers, work, time. Above it, I'm going to put my goal. So where am I trying to land? Below it, I'm going to put my starting or my actual that I've been given. And then if I want to move workers and work, they move together. Work and time would move together. But as you saw in the previous example, workers and time move in opposition. Okay, so let's take 2 minutes and try this one out and let's see how it goes. We'll do 2 more. All right. Okay, so let's start to fill it in. Let me stop our timer. So 9 machines, that's our starting value. So 9 workers at the same rate, they'll always say that, do 27 jerseys in 4 minutes. And you might write what those are, that's fine too, jerseys. And then this is machines. How many minutes would it take 4 machines to stitch 60 jerseys? Okay, so this is the piece I'm looking for. Now everything is up for grabs. My job is to turn any one of these into the other ones, right? So I need to get a 9 to be a 4 or a 27 to be a 60. If there's not an obvious, like, oh, 9 times blah is 4 or 27 times blah is 60, what we'll typically do is reduce one of our columns or both of our columns by the same amount. So in this case, neither of these two are how I want them, right? In the same way, like this one, we already had one fixed. For this one, neither of them are any good. So what we'll do is we'll just go ahead and clean up any one of them. They both seem to be divisible by 9, which actually would get me to a single unit here. So I'm going to divide both. These two move together. So when they're side by side, so workers and work or work and time, they move together. So I'm going to divide both of these by 9. And now I have that one machine can do 3 jerseys this one has to stay the same. I only move 2 pieces at once. Okay, now I can multiply and get to either one of these that I want. So I'm going to multiply this by 4 to get this one where I want it. So I'm going to multiply, and here's the fun part. It doesn't really matter which way you go. It will, in fact, all work out. No matter what, it will always work out. So for this one, this becomes 4 workers. So now it's how I want it, right? So 4 workers is good. It's where I want it. This is 12, still not where I want it. This is still 4 minutes. It's stalled out the way it is. I need 12 to be a 60, but I don't want to move this. So now I'm going to move these 2 columns together. I'm going to keep the 4 just like it is. The 12, I'm going to multiply by 5, which means its neighbor will also be multiplied by 5. So now I have 60, which is, boom, where I want it. 4 times 5 is 20 minutes. And so I have now just answered my question, right? It takes 4 machines, 20 minutes to stitch 60 jerseys. The correct answer is E. Let's do one more. Okay, so you can kind of practice this balancing. Here we go. Again, what you'll do is you'll set up workers, work, and time. Right, so get your workers, work, and time set up. And then above, you'll put the goal, and below your starting value. If they're neighbors, they move together. If they're on the ends, they move in opposition. So we can kind of just move the ratio as we need it. All right. Nice. I got a couple answers in. Very nice. So we'll start with 12 workers pack boxes at a constant rate of 60 boxes every 9 minutes. Oops, put them on the wrong side. Hold on one sec. 12 workers, rate of 60 boxes every 9 minutes. And how many minutes would it take? 27. So I want how many minutes would it take 27 workers to pack 180 boxes? So I have a few different options. This one is a wild card. It can move as much as I need it to. I need to get my 12 to be a 27, which doesn't seem super obvious. I need my 60 to be a 180. That one does actually seem kind of obvious. And so I could scale some of these down, right? Like since these are both divisible by 12, I could, but if I wanted, I could already turn 60 into 180 by multiplying either both of these columns by 3 or both of these columns by 3. I'm going to multiply these two columns by 3. It doesn't actually matter. Right? Like it really doesn't matter, but I'm going to multiply these two columns by 3 because that at least, I don't know, like this one's wonky. I can't get from 12 to 27 anyways. So I'm going to go ahead and multiply this one by 3, but I'll show you that it doesn't matter. I could have done it the other way. So over here, this is now 36. This is 180. So this is where I want it, right? Like I don't want to mess with this one anymore. So this one's where I want it. And this one stays a 9. Okay, so now I need to get 36 to a 27. I don't want to touch my middle column. So instead, I'm going to use my outer columns. I'm going to divide this by 9. Or I want to get something that like I could turn into a 27, right? So actually 36 is 9 times 4. So what if I divided this one by 4? So I'm going to divide this one by 4. And so I'm going to multiply this one by 4. You could have also divided this one by 36, take it all the way to 1. Doesn't really matter. That's going to leave me on a 9 here. 9 times 4 on this side. These are just going to switch places, right? This one's going to become 36. This one is still the 180 the way I want it. I'm going to multiply this one by 3, which means I have to divide this one by 3. And so over here, I get 27, which is where I want it, 180, which is where I want it. And so 36 divided by 3 is 12. That's my answer. What I wanted to highlight for you is sometimes people are like, oh my gosh, which column do I go for? It actually doesn't matter. Right? So I want to show you that I could have chosen differently in my first step. We'll end up doing a lot of the same operations. So if instead of multiplying these 2 by 3, I could have gone ahead and multiplied these 2 by 3. So then I'd keep this 12 the same. So this is 12. Here's the 180. It's where I want it. Now this is 27. Now, I could divide both of these by 4. I want you to note that because you have a calculator, if I needed to and I wasn't sure how to get 12 to be 27, I could just say divide it by 12 and multiply this thing by 12. That's okay too. I'll grab my calculator. 27 times 12. It's kind of a big number. 324. 180. Still the same. This is 1. And now, because they're on the ends, I just have to remember that when I multiply this one by 27, I divide this one by 27. And so we'll grab our calculator again. 324 divided by 27 is 12. So here's my 27 where I wanted it, 180 where I wanted it. Here's 12. That's my answer. So it doesn't matter which one you start with. Yeah. Okay. So friendly reminder, here's our little cheat sheet. If we've got a single person or a machine, we're just going to use work equals rate times time, or we might convert it into the rate equals work over time. If we're working with 2 machines or people working together, we'd add their rates. So rate 1 plus rate 2 equals their rate together. If we are in one of these weird questions, pretty rare, but where they're working against each other, we would use subtraction. And if we've got a scenario where we've got multiple identical people or machines, we're going to do this kind of 2 at a time. And so again, I'll make that note, move 2 at a time, rate, or kind of this like rate ratio. It's a little weird. where I can move workers and work together, I can move work and time together, or I can move workers and time together, just depending on if they're moving together or in opposition, for those when we've got lots of identical machines. Yeah. Just a friendly also reminder that if you haven't done so, we've got free practice exams on our site. So you can go to manhattanprep.com. We've also got a ton of free events, just like this free prep hour. You go to our manhattanprep.com/GRE/classes, and then you get to our free items. So sign up to take any of our live classes. You can take the first session completely for free. So you can come to any session 1 as a trial, totally free. And you'll find that link to the free trial access of a class under this URL. And again, same place, check out our upcoming classes. That first course is free. Right? You can find the full list of all of our classes just at GRE classes. I want to thank y'all so much, and I'm glad y'all are here. I hope you have a wonderful rest of your Saturday. If you're watching the court recording, I hope you have an amazing time studying. Come check out more of our free prep hours here on our YouTube channel. And otherwise, take care.